The Large Hadron Collider is a 27-kilometer superconducting particle accelerator operating at the energy frontier of experimental physics. Rather than observing naturally occurring processes, it creates controlled, high-energy collisions that replicate conditions last seen fractions of a second after the Big Bang. By doing so, the LHC allows physicists to directly test the predictions of quantum field theory and explore the fundamental structure of matter, all at 175 meters below the surface of the Earth. The LHC begins with the simplest possible input, hydrogen gas. Electrons are stripped away, leaving bare protons, which are then accelerated through a multi-stage injection chain, including the linear accelerator, proton synchrotron booster, proton synchrotron, and superproton synchrotron. Each stage incrementally increases energy while maintaining beam equality, ensuring that the protons arrive in the LHC both stable and tightly focused. Inside the Large Hadron Collider, protons circulate in two separate beam pipes, guided by thousands of superconducting magnets cooled to near absolute zero. Dipole magnets bend the beams around the 27-kilometer ring, while quadrupole magnets focus them to microscopic sizes. This precision allows protons to orbit over 10,000 times per second without losing stability. Radio frequency cavities, also known as RF cavities, provide acceleration by synchronizing oscillating electric fields with the proton bunches. Each lap adds a small amount of energy, which accumulates over millions of passes until protons reach energies of several tera-electron volts. At full operation, each beam stores hundreds of megajoules of energy, which is comparable to that of a high-speed train. The two proton beams are divided into tightly packed bunches that cross at specific interaction points. But when protons collide, they don't behave like solid objects. The actual interactions occur between their internal components, quarks and gluons. These high-energy quark-gluon interactions convert kinetic energy into mass, producing short-lived particles, including the Higgs boson, exactly as predicted by quantum field theory. Massive detectors surrounding the collision points record particle trajectories, energies, and decay patterns. Because billions of collisions occur every second, trigger systems instantly discard most events, saving only the most promising ones. This filtered data is then reconstructed to identify particles, such as the Higgs boson, and test theoretical predictions. Experiments at the Large Hadron Collider are fundamentally designed to test the Standard Model, the framework that describes all known elementary particles and their interactions. The discovery of the Higgs boson completed this model, confirming the mechanism that gives particles mass. Today, increasingly precise measurements at the LHC continue to check whether the Standard Model holds exactly or whether subtle deviations point toward the new physics beyond it. In this way, the LHC doesn't just discover new particles, it defines the limits of our current understandings.